we're kind of switching gears now. Like I said, we've been focusing in the beginning of this chapter all on naming compounds, right? Naming them ionically and covalently, and then assigning oxidation numbers to help us name them in different ways. And now we're switching gears a little bit because today we're talking all about how to use a chemical formula. We've been looking at a lot of chemical formulas because as we learned about naming them, we're also learning to derive the formula from the name. But there's more things you can do with formulas. Okay? So today, what I hope you will be able to do by the time we're finished with these notes is calculate formula mass and calculate molar mass for a compound, and then use the formula mass and the molar mass that you have to convert between total number of atoms, number of moles, and the mass of those compounds in grams. And then also, we're going to learn about something called percent composition, and you should be able to use that to determine number of moles or number of grams of a certain element in a compound. Okay? All right, let's begin then. There are 3 valuable characteristics that can be derived by looking at a chemical formula. When we say derived, we mean we can gather that information from the chemical formula. And we're going to cover each of those in detail in our notes today. The first of which is going to be formula mass. You'll recall all the way back in chapter 3 that we learned that all atoms have an average atomic mass. And we give them that average atomic mass in a unit called U, or unified atomic units, and they are on the periodic table for us. Okay? This mass is different, obviously, depending on which element you are talking about. So helium, an atom of helium has a different mass than an atom of nitrogen. Hydrogen has an average atomic mass of 1.01 U, and oxygen has an average atomic mass of 16.00 U. So you can see the differences there. Like atoms, compounds also have a mass, and instead of an atomic mass, or the mass of one atom of that element, we call it a formula mass. You can calculate the formula mass by finding the sum of the average atomic masses of all atoms represented in that compound's formula, hence formula mass. You could call a molecular compound a molecular mass if you wanted to because it's a molecule, but then for ionic compounds it gets a little more tricky, so we use the term formula mass because it covers all our bases. If you're talking about a formula, you can be talking about an ionic or a covalent compound, so we call it a formula mass. For example, if you want to take those atomic masses from the previous slide and use them to calculate formula mass for water, we can do atomic mass of hydrogen at 1.01 U times 2 because there are 2 atoms of hydrogen. And remember, formula mass is the sum of the average atomic masses of all the atoms, not just the elements, but all the atoms represented in the compound. And then atomic mass of oxygen is 16 U. We don't need to multiply it by anything because there is only 1 atom of oxygen. So the formula mass for water, or H2O, would be 18.02 U. You might come up with slightly different values if you rounded your average atomic masses to different numbers, but in our textbook and for the purposes of our problems, we're going to round to 2 decimal places for average atomic mass, so your formula mass should come out to 2 decimal places as well. So, you must know where we're going, since when we did atomic mass, we also talked about molar mass. Okay? Recall from Chapter 3 that the mass of 1 mole of a substance is its molar mass. And we came up with a mole by assigning a mole with a certain number of particles, 6.022 times 10 to the 23 particles of that substance. It's a measuring device like a dozen. Okay? The way in which a mole and a U are defined leaves a nice convenient relationship. This is all refresher. We've talked about this before. Remember that we defined the U by saying one atom of carbon-12 is 12U. So then 1 mole of carbon-12 is 12 grams. So we said that 6.022 times 10 to the 23rd particles of carbon-12 weighs 12 grams. So that many particles is a mole. That's the mass of a mole of carbon-12. All of this information to remind you that this means that 1 gram per mole is equivalent to 1 unified atomic mass unit. So atomic mass and formula mass, therefore, are numerically equivalent. Okay? They're not the same thing, they have different definitions, but numerically, when you're looking at the numbered value of it, they're going to be equivalent, which means you can look to the periodic table not only to get the mass of an element, of an atom of an element in U, but you can also look to the periodic table to find the molar mass of that element. So, since the formula mass of H2O is 18.02 U, then its molar mass would be 18.02 grams per mole of water. So a mole of water would not be just 6.022 times 10 to the 23rd particles, like atoms. It would be 6.022 times 10 to the 23rd molecules of water, which coincidentally means there would be 1 mole of oxygen, but there would be 2 moles of hydrogen atoms present, because it takes twice as many hydrogen atoms to make a molecule of water. The same conversions that we used to convert with molar mass for just atoms of a element can be used with the molar mass of a compound. So, if you'll remember before, if we gave you the mass of an element in grams, you would then have been able to give us the number of moles, and from there, the number of particles, and then you can go the opposite direction as well. You can do the same thing if you're using mass in grams of a compound. As long as you know the formula, you should be able to calculate molar mass and use that to get you number of particles, mass in grams, whatever it is that you need. You can also find the amounts of grams, moles, and particles of a particular element in that compound by looking at the formula. So what I just described to you, that 1 molecule of water has 1 atom of oxygen in it, which means it has 1 mole of oxygen in it. And it has 2 atoms of hydrogen, so it would have 2 moles of hydrogen in it. And you can use that to help you convert as well, which we will do practice with. So, let's look at a practice problem. I want you to answer the following questions about a bottle of ibuprofen. Okay? Keeping in mind that the formula for ibuprofen is C13H18O2. So, given that, I want you to tell me if there are tablets in this bottle and the total mass of all those tablets is 33 grams of ibuprofen, how many moles of ibuprofen are in the bottle? Then I want you to calculate for me how many molecules of ibuprofen are in the bottle. And then I want the total mass in grams of just the carbon found in 33 grams of ibuprofen. So I'm going to give you quite a bit of time to work on these problems, and then we will run them on the board. Let's start with number 1, or letter A, I should say. So, we need molar mass in order to solve this question. So we can calculate our molar mass by taking the molar masses of each atom, multiplying by the number of each atom, and then adding it up. So molar mass of carbon is, anybody know? 12.01 grams per mole times 13, because that's how many of them there are, and that comes out to what, roughly? Anybody who did the math? 156.13 grams per mole. Okay, then we have hydrogen, which has a molar mass of 1.01 grams per mole, times 18, because there are 18 of them, so we should come out with just 18.144 grams per mole. And then oxygen has a molar mass of 16 grams per mole. And times that times 2, we get 32. Yeah? Am I doing my math right there? 32 grams per mole. And then we will sum all of this, and it comes out to like 206 point something, right? 274 grams per mole. So this is our molar mass. It doesn't answer the question yet, but it gets us partway there. Okay, so now we know that if we had 1 mole of ibuprofen, it would weigh in grams 206.274 grams. But we don't have a whole mole of ibuprofen, do we? Because the sample that they gave us, they said only weighs 33 grams. So we have nowhere near 1 whole mole of this. So to calculate how many, we will take that molar mass and use it. So we have our given mass times 1 mole of ibuprofen, which we know weighs 206.274. Is that what we said? Grams. And when we do this, what we wind up doing is we cancel out the grams, and 33 times 1 divided by 206.274 comes out to what? Yeah, 0.16 moles. So we don't have a whole mole. We have less than 2/10 of a mole, right? We have 0.16 of a mole of ibuprofen. Okay. Take this answer we just came up with and use it for part B. Okay? So this right here, moles of ibuprofen, is the starting point for your next problem. So give that a shot.